So we just learned how to find pulsars using the so-called single pulse method, which was used, of course, to find the very first pulsars and has become very common in pulsar searches these days, and actually led to the discovery of the exotic objects called fast radio bursts, which may or may not have any association with radio pulsars or neutron stars in general. So now what I want to do is I want to talk to you about the sort of ubiquitous or the most common technique for finding pulsars that has been employed over the last few decades. This is using the fast Fourier transform. The fast Fourier transform is incredibly useful for finding pulsars because, of course, they are highly periodic. And normally you would expect that when you do the fast Fourier transform, which I hope you are familiar with, that if you have a sinusoidal function, then you would expect to see a peak in the Fourier spectrum at the frequency of the pulsar. And remember, the frequency is proportional to 1 over the period, or it's actually equal to 1 over the period. So if we have a pulsar with a period of 1 second, then we would expect to see a peak in the Fourier transform, the Fourier spectrum, at 1 hertz. Now, as I showed you, pulsars are narrow objects, okay? So they emit for only a fraction of the rotational period. And so what that means is that you need many, many sinusoids to be able to model that pulse shape. And that means that you get lots and lots of harmonics. And you can actually see these harmonics in the bottom left-hand plot here, which is the spectrum. It says frequency, it says frequency against power. And we'll come back to discussing that in a moment. So how does searching using the fast Fourier transform work? Well, here you can see an overall flow chart of this, and I'll make these slides available so that you can look at this in more detail if you'd like to. But first we start off with the similar procedure to what we discussed for the single pulse search, where we take the raw data from the telescope and we clean it from interference. So we remove the radio frequency interference. The next step is we do the de-dispersion, and we need to do the de-dispersion at many, many dispersion measures, as we did for the single pulse search. And then after the de-dispersion, we take the Fourier transform of the data. And so we take the time series, the de-dispersed time series that we see here, and then we perform the Fourier transform. And when we do the Fourier transform, we turn our time series into a frequency series, okay? And so here you can see the frequency, and here you can see the power, so how much strength is there in the signal. And the peak at 0 corresponds to the offset of the data from 0 in the time domain. But then you can see these peaks here at 2.5 hertz, 5 hertz, 7.5, 10, and so on. And the 2.5 hertz signal is what we call the fundamental, or sometimes people will even call it the first harmonic. And so that corresponds to 1 over the period. Okay, so this is like approximately a 400 millisecond pulsar. And so you can see that it has a number of harmonics. So there's another pulse at 5 hertz, 7.5, 10. So they're equally spaced by the frequency of the source. And the number of harmonics tells us something about the shape of the pulse profile. So then once we've got the power spectrum, you'd notice that it had this, the Fourier spectrum, it had this curve up to lower frequencies. Now that is something called red noise. And we think that's due to fluctuations in the receiver and in the sky that are not associated with the pulsar. And so we need to try and remove that to make it easier to detect our signal. And so there's a process called de-reddening, and that's what's been done here to these data. And so now we need to do a periodicity search. And to do that, if we want to gain the maximum return from our signal, we want to add all of these harmonics together. Okay, and we do that is a process we call harmonic summing. So we chop the spectrum into pieces and we add them together to try and increase the signal due to the periodic nature of the pulsar. And so again, we use something like the threshold technique, which we used in the single pulse search, but now we're doing it in the frequency domain. And here I have just labeled those harmonics that we were talking about earlier. Excuse me. So now we need to do something called candidate optimization. And what that basically means is that we take that best frequency that we discovered from the Fourier spectrum and we turn that into a period. And then we fold, remember that folding process I showed you earlier when we were talking about pulsar timing, we fold the data at that period. And what we can see here in the left-hand plot is an example of that. So you can see we folded the data into short periods of time, and then we stacked them one above the other. And if you've got a real signal, you expect the pulse to line up nice and straight in here and be nice and clear in the pulse profile at the top. So this is the average pulse profile, which is the sum of all of these different integrations. You'll also see there's still some radio frequency interference in these data. These data are actually from the GMRT. And so, you know, ideally we would like to have cleaned that out to improve the quality of the signal. Similarly, here in this plot in the middle, we've now got frequency against the pulse phase. So that's one, well, in fact, here we show two rotations of the pulsar. So that's why you can see two peaks. So they're not separate peaks. This is because we've just shown two, because sometimes it's easier to see things if they are repeated. And you can see that it's nice and straight in frequency, which means that we've corrected for the dispersion perfectly. And then I'll just tell you about one more plot here. The others are a bit more advanced, and we could touch on those if anyone has any questions. But here we show the different dispersion measures that we tried. So remember, we try all these different dispersion measures, and you can see on the left-hand side, we use something like the reduced chi-squared, which is basically like a proxy or something we can use instead of the signal-to-noise ratio. And here we can see that we get a nice peak at the correct dispersion measure. So now we've got our candidate and we've optimized it. And then we'll go away and we'll use this optimized value for preparing the data that we might send to a machine learning classifier. So we use quite often machine learning or artificial intelligence to try and work out whether a candidate is a real pulsar or not. And the reason we do that is because we end up with thousands and thousands of candidates, and it's impossible to view them all by eye. So that was the basic process of searching for pulsars using the fast Fourier transform. Another technique which was first proposed right back at the start when pulsars were first discovered in the 1960s, but fell out of favor when the fast Fourier transform came along, but is becoming popular again because of its potential for allowing us to find longer period pulsars with narrow pulse profiles. And we think that there's a whole population of those pulsars that have not yet been discovered. So how does this process work? Well, we start in the same way. You could see that was the same as we had for the single pulse search and everything. We start with the same data. We do de-dispersion at multiple trial dispersion measures as before. Sorry, let me just step back. Yeah, and so this is quite a bright pulsar just to demonstrate the process here. It works also for very weak pulsars. And now the difference between doing the fast folding algorithm and the fast Fourier transform is that the folding algorithm is really just trying lots and lots of different periods to fold the data at. And when you do that, you get a 3D cube, which is a combination of pulse width. So we convolve the data with a template, which tries to match the pulse width, the pulse period, and then against the signal to noise ratio. And we look again for distinctive peaks in this region to try and identify. So here's the peak detection, again, showing us everything above this line we think is a potential pulsar. So then we simply have the period. We know the period and we know the dispersion measure. And so we do a similar technique as we did for the fast Fourier transform, where we fold the data using this new period and this new dispersion measure, and we try and optimize it. Now, the advantages of the fast folding algorithm is that it uses all of the information. I mentioned to you about doing this harmonic summing that we do in the fast Fourier transform. Typically, we only can add a few of those harmonics. And when we add those harmonics, we do it incoherently. And so we lose some of the information. If we fold the data with the actual period, we get all of the information we possibly can. And so it allows us to search for fainter signals. However, it's computationally expensive. And so we tend to only use it for the longer period pulsars. So anything maybe around 500 milliseconds or longer. So the next question is, where should we look? Where should we look for pulsars? What's the best region of sky? Now, you can see here the same graphic I showed you somewhat earlier, which shows where the pulsars are in the sky. Now, you could go ahead and search in the plane, which is where most of the pulsars are. The question is, are you going to find new types of pulsars then? And by comparison, if you were trying to find millisecond pulsars, you can see that they are more isotropically, more evenly distributed across the sky. And so you might want to do a blind all-sky survey. On the right-hand side, I'm showing you a version of the model that I showed you earlier for the dispersion measure, so the electron distribution in our galaxy, and overlaid are all of the known pulsars. Now, the black dot here is where the sun is. And so you can see that we're seeing pulsars, you know, in a reasonable fraction of the galaxy around the sun, but there's still a huge amount of the galaxy that we're not able to reach. And so that might suggest that we should go, you know, we need more sensitive telescopes, or we need to go to higher frequencies to beat the influence of the dispersion measure. So what about all sky surveys? Well, the advantage of the all sky survey, as I hinted at before, is that it gives you an unbiased view of the population of pulsars in the galaxy. However, it takes a long time, and in many locations you won't see anything. So it takes a lot of telescope time, a lot of computing time, and so you may not find anything. So what about a targeted search? So where you look in specific directions. The disadvantage is that it gives you maybe a biased view of the population, because you sort of look where you think you will know there's a pulsar. But the advantage is you can optimally use your observing time and increase your sensitivity. A particularly interesting region to target is the galactic center, because we think there should be a lot of pulsars in the galactic center. And certainly the galactic plane is somewhere we should also look, because you can see here some of these beautiful supernova remnants that are marked out here. And we think that, you know, these, of course, should be the location of young and energetic pulsars. The galactic center is particularly interesting also because we would like to try and find a pulsar orbiting a black hole at the center of our galaxy. We can also look in globular clusters. So globular clusters are regions where there are vast numbers of stars that I hinted at before, and we know that you get lots and lots of millisecond pulsars in globular clusters. In fact, in the two clusters I'm showing you here, 47 Tuc and Terzan 5, combined, there are nearly 60 millisecond pulsars. So nearly 10% of all of the known millisecond pulsars are located in just these two globular clusters. And we also expect we might get quite exotic objects in these clusters because of the collisions that happen, or the exchanges between different binary systems due to the density of stars that are located here. Another potential location to look are these high energy sources. So detected by telescopes like HESS, they emit tera-electron volt gamma rays. These are associated with so-called pulsar wind nebulae, where we expect to see the interaction between the pulsar and its environment. And so it might be, again, a signpost as to where we expect these pulsars to be. Again, it might be a location for young pulsars in particular. And perhaps the most successful of all of the targeted approaches has been to look at gamma ray sources identified with the Fermi Space Telescope. Now, Fermi looks in gamma rays. You can look at the spectrum of the gamma ray sources, and that hints, or actually it's a very, very good indicator of where you might expect to find a millisecond pulsar. And so you can find all these regions in the gamma rays, and despite the fact that the gamma rays are not particularly well localized, it still gives a nice pointer. And so far you can see somewhere around about 80 of these very interesting so-called millisecond pulsars have been found using this method. So it's been extremely successful. So the question would be, why should we search for more? Well, we hinted at some of this right back when I was telling you about how useful pulsars are. So for doing all of these different studies, we would like to find more sources. And in particular, you typically want to find sources that are at the extreme edges of the current known population. We want to fill out this so-called period derivative diagram that we talked about before. And I'll actually just pause here for another break in the video. And then we'll come back and we'll talk about more details about why we should search for more pulsars.